Okay, so how is everyone today? Good, I hope. It's come to my attention that that there was some kind of glitch or I don't know what with Box over the weekend, and for a small group of students, it was not possible for you to access your papers. So under, if there was no glitch, then today 150 and 151 would be due. But because this glitch affected a small number of folks, then we're going to move the due date of 150 and 151 to Wednesday, 2 days from now. But if you brought it and you just want to turn it in right now, that would be fine. I'll put it right here.
Professor McCary, sorry, can I ask a brief question?
Yeah.
Are any of the weekly homeworks graded and uploaded yet, or is that waiting to happen? I'm just curious because I've gotten new grades for the online ones, but none of the return, and it causes a little anxious.
There should be scanned and available on this in the directory right next to the, yeah.
Okay. Are they graded there?
Well, yes and no. Can we ask after? Can we do this after class?
Yeah.
All right. So last time we were talking about domain, and we've still got plenty of stuff to say about domain. So just to briefly recap what we said last time is that to some extent the expressions that we write down, they're like machines. Are like machines with inputs and outputs. In the following kind of sense. So here's an example. We could say, well, concerning the expression, say 13x plus 14. So it's an expression, and you could say, well, what if you give it input x equal to 10, say, which is kind of a strange way to say, well, what do you get if you plug in 10? Then in that case, the output would be, you plug in 10, so that'd be 13 multiplied by 10 and then plus 14, and then do some arithmetic and get 144. All right? And if you plug in a different value, you could very well get a different output. But you won't necessarily always get a different output because, for example, x squared is an expression, and what do you get if you plug in -4? 16. And what do you get if you plug in +4? 16. All right. So the domain of an expression is the set of inputs for which it is defined. Okay. So, to give an example, I could say something like, how about x squared, 5x squared, say, plus 4 with domain x greater than 2. So that means that, concerning this expression, when we're using it, it's only allowed that you should plug in things more than 2. So you can't plug in 2, right? Because 2 is not more than 2. But you could plug in 3. If you were to plug in 3, well, that'd be 5 times 3 squared plus 4. So 5 times 9 is 45, and then 4 more, that'd be 49. But, if you ask to plug in, x is 2, what's the correct way to respond? That this is not defined. Now this seems a little bit, because it's like just language and abstract. It can seem kind of strange to say that here's a machine and that's the kind of inputs that we accept. When in some sense you can clearly see that if it weren't for that, then there'd be no prohibition of putting a 2 in there, or anything else for that matter. But right around the corner there's a vending machine. And, ignoring the buttons you have to press, it's a machine that you put money in and candy comes out. That's what it is. But the thing is, it doesn't accept just any kind of money. It accepts U.S. currency. And in fact, not just any kind of U.S. currency, only certain denominations. Because I haven't verified this, but I feel pretty certain that it doesn't accept $100 bills. It just probably doesn't do that. But it does, I imagine, accept quarters. Okay, so then you could look at it and say, well, I don't understand why it doesn't accept a $100 bill. Well, it says on there that it doesn't, right? Or you could say, well, I don't understand why it doesn't accept a check. Well, it just doesn't, right? Okay. So, 3. When the domain is not explicitly given, the domain is the natural domain of the expression. Domain has an A in it. Natural domain of the expression. Okay, and we defined that term last time. What is a natural domain? Right, the largest set for which the expression is defined. So you can, I don't think such a thing exists, but you can imagine there being a vending machine that accepts currency in every conceivable form. Right? Like, I've never seen a $1,000 bill, but I understand that they exist. And you can imagine a vending machine that accepts a $1,000 bill. All right. Fine. Good. So here's an example question of how this comes up. So, but before we do the example, I'm going to write this hidden block. So this is like me working back in my office trying to make an exercise for you. All right. So this is going to be an exercise that's like the last exercise that we did last time, except it's going to be a fuller experience of doing it. So first, I'll say, okay, I'm going to do 2x plus 3 multiplied by x minus 6. I'm going to multiply this out and collect like terms. So that'd be 2x squared minus 12x plus 3x minus 18. and then simplifying this, that'd be 2x squared minus 9x minus 18. And then I'll do something similar. I'll say 2x minus 5 times x minus 6. And multiply this out and collect like terms. That would be 2x squared minus 12x minus 5x plus 30 is 2x squared minus 17x plus 30. And again, this is me. You can imagine that this is like me back in my office making an exercise for you, and you wouldn't, under normal circumstances, see this. But the point is that I want to make a question that that looks like this, like quadratic over quadratic. An expression that sort of has that form. So here I just made two quadratics. Okay, so here's the question. So let 2x squared minus 9x minus 18 over 2x squared minus 17x plus 30 be called A, just so we can refer to it by name. So let that be the case. So now there's two requests. First is simplify A by cancellation. And two, find the domain of A. All right, and these are part 1 and 2 are definitely related. All right. So we want to simplify by cancellation. So what do we need to do to do that? So I guess my first question is that as it's written, as it was given, like this, is there any cancellation that's sort of immediately obvious? No, there isn't. Now, you might look at this and say, like, well, it looks to me like we've got a 2x squared over a 2x squared. Do those cancel? And the answer is no, because these are terms added together in the numerator, and these are terms added together in the denominator, and they're being divided. So you know, multiplication distributes over add, but division doesn't. So there's no like cancellation that you can do immediately. What do we need to do? We need to factor them, right? We need to factor. So for one, in fact for both, for both 1 and 2, we need to factor. Expression A. So here's the deal. The last exercise that we did last time was just like this in the sense that it was a quadratic divided by another quadratic. But that one was easy because the quadratics were easy. Okay, so then now this isn't part of the solution to the exercise, but this is an appropriate point, I think, to write down the policy for factoring, for showing work for factoring quadratics. So here's the course policy. for showing work for factoring quadratics. All right. So one notable difference between the quadratics at the end of last time and this one is that at the end of last time, those quadratics were monic. So what does that mean?
The leading coefficient was 1.
The leading coefficient was 1. And also, it was the case that the factorization was sort of obvious. So the fact that they were monic and you could look at it, you could just sort of just in your head real quick say, can I think of two numbers that do that? And then, yeah, it's just immediate. Okay, so then here's the definition. So, so we'll call a quadratic easy easy if two requirements. If it's monic and factors over the integers. Okay, so a few examples would be good. So one example would be something like, how about w squared minus 13w, and then now I'm going to come up with two numbers that add to negative 13. So how about negative 17, and then add 4? That'd work, right? So if I do that, that'd be negative 68. So, you know, here's an example where this one is easy. It's easy because it's monic, and, you know, the numbers are such that you can really quickly run through all the possibilities, right? What are the divisors, for example, what are the divisors of 68? Well, 1 and 68, that's not going to give me 13. 2 and 34, that's not going to do it. 3, nope, 3's not even a divisor. 4, oh, that one works. Right? You can just sort of see it. 4, and then you have got to do a little calculation in your head. 4 and 17, it does work, right? So this kind, I'm saying that this one is easy enough, that this one is easy. It's immediately obvious that it's w plus 4 multiplied by w minus 17. So, you know, this one is easy. If I take a really similar one, w squared minus 13w, and then change that to like minus 69, say. Now, sort of, you might say that these seem really similar to each other in the sense that the only difference is that that number is 68 and that one is 69. But you can now run through the factors of 69 and try and figure it out. So, you know, writing it down, 1 and 69. Can I get those to be 13? Nah. 2, that one won't work. 3 and 23. Can I get those to work? And in fact, that's the way that 69 factors because 23 is prime. So there aren't going to be any other integers that do it. So can you see that, you know, there's only 2 pairs available, that pair, and you're not going to be able to get it to work. Okay, so this one is not easy. This one. Okay, and then finally, if I take that same one and you know, write w squared times 13w plus 13w, I mean to say, and then minus 68. So right, oh man, I'm having so much trouble. So I'm trying to copy that same one. W squared minus 13w minus 68. So far I've just copied it, but now I'm going to put like a 4 here. So now it's not monic. Okay, so according to our definition of this word, easy, this one is not easy. So to be easy, it has to be monic, and the factors have to be integers. All right. So in that case, here's the policy: is that P1 is that if the quadratic is easy, then no work is required. So what I mean is that, if you're faced with, say, z squared minus 11z and then plus 30, say, then I claim that this one is so straightforward that you just write down the answer. So what is the answer? Right. So you can kind of just quickly run through the factors of 30. And can you get two factors to get you 11? 5 and 6 will do it if they're both negative, right? Okay. So this is the kind that I'm saying that, just write it down. Now, don't interpret this as me saying that you're not allowed to do work. By all means. I'm just saying that it's not required in such a case. So then otherwise, you must show work. Okay, so any question about the policy? So, in the end, you might kind of wonder, why is this a policy? All right. Here, what I'm saying is that in the case of an easy one, an easy quadratic that's monic and factors over the integers, that's more or less just like me asking for you to factor 35. And I don't need you to show work to tell me that it's 5 times 7. It just, that's straightforward enough. I'm saying that this is a similar kind of situation. But if I ask you to factor some number that's got, a bunch of digits in it, like it's in the thousands or something, then I need you to do a little bit of something. Show some work. All right. So all of, interpreting that, what that means essentially is that, we're going to have to factor A, and notice that there's this quadratic and that quadratic, and neither one of them is easy, which means that we have our work cut out for us. So can you see the implication? All right, so let's do it. So factor the numerator. The numerator is 2x squared minus 9x minus 18. All right. So then we're looking for two numbers, p and q, and those two numbers have to satisfy two constraints. So one constraint is that the sum needs to be what? -9. And the product, the other constraint is that the product needs to be what?
36.
Okay, so how are you getting -36?
162. You have to multiply the 9 and the -9 and -18.
So it's not the product of these two, rather it's the product of the first one and the last one. Yeah, the first and the last. So it would be 2 multiplied by -18, which is -36. Okay. So we want two numbers that satisfy both of those constraints. Now, it's not really necessary to think of this because that's enough work. That's enough hints to go on. But I'll continue to mention that because the product is negative, and because we're looking for two numbers and the product is negative, that means that it has to be the case that one is negative and one's positive. Because if you select two positive numbers, the product's going to be positive. And if you select two negative numbers, the product will be positive. So you need to select one negative and one positive. And because the sum is -9, that means that the negative one has to be bigger. It has to win, so that when you add them, the result is negative. Okay, so, to remind you of what this is about, I'll make a choice, but it's not a winner. So this is, it's not a winner, but I claim that it's at least reasonable in one way. Why is it reasonable in one way? Yeah, because the sum's right. Okay, so that's good. But then the product is -10. And that's not good. Okay, but you do enough of these and it starts to become kind of clear. Can anyone give us a good idea of what two numbers we want? What was it? Okay, so -12 and +3. So checking that, the sum, that's good. And the product, that's good. So we found the pair of numbers that we're looking for. Now if we were, yes?
Isn't 2 times -18, I just answered my own question, never mind.
Okay. Like I think I even mentioned that a couple weeks ago, right? It happens all the time, is that, if you ever find yourself being a tutor of any kind, a really good technique, even if you have no idea what you're actually teaching, is that can you like restate the question for me in a sentence? And just the action of the person saying it out loud is often enough for them to say, never mind. I see it. All right. Fine. So then if we were factoring a monic quadratic, then we would at this point just immediately say that the factorization is x minus 12 times x plus 3. It would just be done. In fact, we wouldn't even have done this table according to the course policy unless you just really wanted to do the table. But we're not factoring a monic quadratic. We're factoring a non-monic quadratic, which means that what is the purpose of these two numbers?
Separate the x.
Yeah, we want to split that term in the middle. That's the purpose of those two numbers. So we're going to take 2x squared minus 9x minus 18. Now, as written, that quadratic, how many terms are there? There's 3. And the purpose of those numbers is so we can split this term into 2 so that, in some sense, there'll be 4 terms. So specifically, what I'm saying is that we're fine with that first term, we like that one, and we're fine with the last term, we like that one. But the point of these two numbers is that we're going to use them to split that into 2 bits. We're going to say that, okay, first, to get -9x, first we're going to subtract 12x, and then after that we're going to add 3x. All right. Notice, just for those of you that like to pay attention to this kind of thing, back in this place where that is the hidden bit. Do you observe that through this work we've reconstructed that? That's taking one step backwards. All right. Now, to take the last step is to observe that, okay, now that we have 4 terms, we can make 2 groups of size 2. 2x squared minus 12x is the first group, and the second group is 3x minus 18. Now, in each group, there's a GCF, a greatest common factor. So in the first group, what's the GCF? 2x. And in the second group, what's the GCF? 3. Now, before I fill in these parentheses here, we should have a definite expectation about what will happen. What should happen? They should be the same. They should be the same. So for this first group, ignoring the second group, if we do that, what do you get if you factor out 2x? X minus 6. And so now, because we expect them to be the same, we know that's got to be x minus 6. But in order not to pollute my, the opportunity here, I have to check. I'm going to cover that up and say, all right, what do I get if I factor out 3? X minus 6. And then take a look and say, all right, that's right. Okay, if we had gotten anything else, then that would be a signal that we made an error. Those have to be the same. Now, here on this line we had 3 terms, and then we split to 4 terms, which allowed us to have 2 groups of size 2. And now on this expression, covering this up, again, or not again, but now observe that there's 2 terms. There's 2 terms, and what I'm covering up is the same. That's what's relevant. So if I happen to be covering up something like z squared w, so if this is z squared w and that's z squared w, if they're both z squared w, then we could factor it out. And if they were both a banana, we could factor out a banana. All that matters is that they're the same, and they're both x minus 6, which means we can factor it out. So, like this, x minus 6 factors out. And what do we write right there? 2x plus 3. And again, just for you like to follow along, essentially what we did is we started here. We did a search for 2 different numbers so that we could get there. And then we did a grouping, GCF, blah, blah thing to step there. So going that way is more difficult, more difficult than going that way, right? But that's the way the world is. Walking downhill is easier than walking uphill. What am I looking at here? So we factored the numerator. Now we need to factor the denominator. Okay, so now I'm gonna make an error on purpose. So don't call it out if you see it immediately. Okay, so I'm gonna factor the denominator, and it is 2x squared minus 17x plus 3. Okay, so we want to factor the denominator. So that means that we're looking for 2 numbers. Looking for 2 numbers, and they have to satisfy 2 constraints. The sum needs to be negative 17, and the product needs to be what? According to what I've written. 6, right? Because it need to be 2 times 3. And now, when you've gotten to a place on this kind of work where you're starting to get comfortable with this, I claim that you should look at this and immediately think, nah, that can't be right. So, can anyone put it into words? This couldn't be right. I claim that something about this table, this thing that we're searching for, is saying that no, that's not going to happen. Can anyone put it into words? Yeah. Is that, you know, we need a product and we need a sum. And like that product is little, you know, and the sum is like big. And so, you know, imagine all the ways you can factor 6 with integers. There's not that many, right? There's like 1 and 6, and there's 2 and 3. So if you had 1 and 6, can you get that? Can that add up to 17? No. What about 2 and 3? That's even worse, right? So I claim that looking at this, as it's written there, you should immediately think, nah, something's not right here. Okay? So, you know, writing it down, I could say, well, I'll try 1 and 6. Now that has the virtue of giving 6. That's good for the product. But for the sum, that's 7. Okay, that's not going to work because, among other things, the sum doesn't even have the correct sign. So I'll try, well, okay, how about -1 and -6? So that has the virtue of still having the correct product. And now the sum is -7, so it has the correct sign, but it's still not the correct value. You know, and then maybe just one more to sort of drive it home. That has the virtue of having the correct product, but now the sum is even worse. It's even further away. So can you see we're not gonna make it work. So you know, the product looks too small. The factors will never add up. To 17, either positive or -17. Okay, so this is the kind of, you know, this kind of error. So I've made an error. There's you know, there's nothing wrong with the question. It's just I've made an error, but this kind of error is extremely common, and you need to be able to identify when you've gotten in this position to think what could have possibly gone wrong. Okay, so what did go wrong?
30, not 3.
Yeah, is that I copied that number as a 3, but it's a 30. It's just, you know, it's not a big deal, but it can be completely befuddling on a quiz if you're sitting there looking at that 3 thinking, no, this can't possibly work. Okay, so in the end, is that that should be a 30. Not 3. All right, so let's try again. Factor the denominator. (2x² minus 17x) and then plus 30. All right, so we're looking for two numbers, and we want the sum to be -17, and we want the product to be 2 times 30, which is 60. And now, in comparison to this one, I claim that this feels a lot better because there's a lot more freedom with 60 than there is with 6. Okay. So, you know, just to give one that doesn't work, how about -30 and -2? That one has the virtue of the product being right, but the sum is not. So yes, yes, yes. No, no, no. No, yes, like that. Another one, I'll make the sum right. So here's a particular, for this particular one, here's one that I would expect a lot of students to bite on incorrectly. How about -20 and +3? So why is that one reasonable? Yeah, the sum's right. And what's the product? negative 60. And what product are we actually looking for? Positive 60, right? So is that the one we wanted? It's not. Nevertheless, you know, I'm just reporting to you that a lot of students on a question where this is the situation are going to take that one. All right, so then, you know, we've you know, messed around here enough. What's the pair that's going to work?
Negative 12, negative 5.
Very good. Negative 12 and negative 5. Sum's good. Product's good. Any question about that? All right, so now exact same trick. The purpose of these two numbers, okay, it's a split. The middle term is to cause a split. Okay, so then we'll have 2x squared minus 17x plus 30. And now we want to make the split, so this will be 2x squared minus 12x minus 5 more x's plus 30. Now that we have 4 terms, we can make 2 groups of size 2. So 2x squared minus 12x, and then plus negative 5x plus 30. All right. So now that we have 2 groups of size 2, we want to factor the GCF out of both groups. All right. So because I want to illustrate something, I can see that the GCF is 2x. Fine. And then for this other one, I can see that in some sense there's kind of like a choice. We could, you know, we can't get any x's out because that one doesn't have any x's. But the coefficients are both divisible by 5 and negative 5 also. So you might think, okay, well, it seems kind of like I have a choice between 5 and negative 5. Which choice should we make? Okay, in the end, I'm gonna choose one of them first. I'm gonna say, okay, well, suppose I factor out 5. Then because of what we're doing, we have a definite expectation about what's going to happen with these. What's our expectation? They're going to need to be the same, right? That's how we'll know that we're on the right track. But you know, suppose that, you know, I made a choice. It wasn't clear. It was sort of like a 50-50. I made this choice. Let's see what happens. So if I factor out 2x, then for this one I get x minus 6. And what do I get for this one? I get negative x plus 6. So is that what we wanted? It's not, right? So can you see these are not the same? So that should be, you know, a signal to you that, oh, something's not right. In the end, it's because there were 2 choices. We could have factored out 5 or negative 5, and we tried 5, and that wasn't the winner. Okay, so then 2x times x minus 6 like this, and if we factor out negative 5, ignoring that, then what do you get if you factor out negative 5? X minus 6. So can you see how this position is a nice marker? All right. So then again, we have the same thing twice, so we can factor it out. So the answer should look like this. And then what goes here? 2x minus 5. And again, just for those of you that like seeing the question from this point of view, you know, we started with this, And then we did the search to split that middle term like that. And then we did two groups of 2 in a GCF thingy to step from here to there. All right. But notably, concerning this exercise, we actually haven't answered either one of the questions yet. It seems like we've been doing this forever, right? Fine. Question number 1 was simplify expression A by cancellation. And what we said is that in order to do that, we need to factor the numerator and denominator, and we've achieved that. So as a result, here's expression A, 2x squared minus 9x minus 18 over 2x squared minus 17x plus 30. So that's what was originally given. And we just established that the numerator factors as 2x plus 3 multiplied by x minus 6, and the denominator factors as 2x minus 5 multiplied by x minus 6. So all that work to establish that. So is there any cancellation possible? Yeah, there's x minus 6's, right? Those cancel. And you know, if it had come to pass that there weren't any, then you would say that there is no cancellation possible. That's totally reasonable too. I could have arranged it to where instead of it being x minus 6, we could have made it be x minus 7. All right, but you know, there is some cancellation. So 2x plus 3 over 2x minus 5. All right. So now the second question was find the domain of A. So there was no domain explicitly given. So no explicit domain. No explicit domain. Therefore, we're going to use the natural domain. Now, again, concerning the natural domain, that's the largest set of inputs for which the expression can be defined. And in our class, currently, for the expressions that we're using, there's only 2 ways things can break: division by 0 and negative inputs to even radicals. Now, there are no radicals whatsoever, so it can't break because of that. But conceivably, we could divide by 0, so that could be a problem. So we must avoid the denominator equal to 0. You know, so that's what we have to avoid. So we need to figure out, well, when could that happen? All right. So to speed things along, I'll offer something. So in the first place, it seems to me that if 2x minus 5 is ever 0, that'd be a problem. Okay. So I'm going to solve 2x minus 5 equal to 0. So that's saying 2x is 5, and that's saying that x is 5/2. So if x is 5/2, I'm saying that that's a problem. So I'll start writing something else and say that therefore the domain is all reals except x is 5/2. But this is not right. Let's not write about this.
You also have to include the factor
Right. So, 6 can't be allowed either. Now, concerning this expression right here, what is the denominator when you plug in x is 6? What's the denominator? 7. Is it okay to divide by 7? Yeah. You might have, you might not particularly care for 7s. I don't know why you would have such a preference, but there's nothing mathematically wrong with that. But nevertheless, I'm saying that it is not that we can't include 6 because it has to do with the question. The question says, find the domain of expression A. Is that expression A? It is not. That's expression A. And what do you get for this denominator if you plug in 6? 0. Okay, so then we also need that one. So x, so solve that one as well. So x is 6, except that and this one. So can you see the distinction? So I just bring this up because all the time many students will successfully get to here and then flub this last bit. All right, so that's all that we have for today. I hope you have a wonderful Monday. If you wish to turn in 151 now, then you can do that. Otherwise, you can turn it in on Zoom.